Okay, well, I'm started on chapter 16, just to backfill a little bit. Chapter 16 is about confidence intervals. It starts off with a little introduction or a review of the properties of the sample mean. So let's look at that for a second. So here's x bar, the sample mean. It says the mean for the sample mean is the mean of the population you're sampling from. Sigma of the sample mean is sigma of the population you're sampling from divided by square root of n. And x bar has an approximately normal distribution if n is large. That's called the central limit theorem. And x bar is exactly normal if the population is normal. So that's just a fact about sampling from normal populations, that the sample means come out normally distributed. So we're going to do a couple of example calculations, so we just get back in the swing of how x bar works. Here's some calculations with x bar. The first one is, suppose the sample size is 20, and the mean of the population is 100, and the standard deviation of the population is 2.6. Let's find the probability that x bar is bigger than 101. So the way I usually start this off, I draw the picture of the distribution of x bar, so I know approximately what's going on. So here's x bar here. Its mean is 100, which is the mean of the population. Here's the standard deviation, it's 2.6 over the square root of 20, which is 0.58. So that means if you go from 100, the distance is 0.58, that's one standard deviation. So you mark it off, 1, 2, 3 standard deviations like that. 100.58, 101.16 is 2 standard deviations. 101 is between these two values, pretty close to that one. And we want the probability x bar is bigger than 101, so we want this upper tail probability for the distribution of x bar. And the plan is to compute a z-value. We know x bar is normally distributed, so we can compute z. We put value minus mean over standard deviation. The value we're interested in is 101. The mean is 100. Here's the standard deviation for x bar. To compute that z-value, we should write it here maybe. So z for x bar looks like x bar minus mu over sigma over root n. That's what we just did. We get 1.72. So 1.72 is in this same position, and the normal distribution as 101 was for x bar. We go to the table, so that's z, so that's standard normal. So we go to the tables, we look up 1.72. We'll get 0.9573 as the chance of being less than 1.72. We want the greater than chance, so we do 1 minus 0.9573. 1 minus 0.9573 will be the probability z is bigger than 1.72. The upper tail probability is at 0.427, and that tail probability matches the probability for x bar. So the probability x bar is bigger than 101 is also 0.427. So there are some example calculations for x bar. We'll do a couple more because we're going to use x bar as our basis for building a confidence interval. So we have to really understand how it works. And more or less the thing we're considering is how close x bar tends to be to the population mean 100, since we know what its distribution looks like. So we'll look at that a bit more in a minute. And there's a lot of pages to chapter 16, it turns out.